Hello and welcome to the first video I've made in a while. I just kind of got the motivation to make a video and wanted to share something that I've been enjoying in my professional life, and yeah, I thought it would be cool to share. So the topic of this video is basically talking about building an HTTP server in Rust. But also, I wanted to take it from the perspective of a JavaScript or a TypeScript developer, mainly because Rust is an intimidating language that a lot of people feel hesitant to jump into, mainly because it has a reputation for being very complicated. And it is a complicated language, but after using it for a while, it's honestly, it feels a lot more like TypeScript than it does than C, for instance, or C++. It is extremely simple, and you only really ever touch the really complex parts when you need to do something that drills down deeply into performance optimizations. Pretty much all the weird things about Rust you can deal with in very simple syntax, and it looks exactly like TypeScript or very close to. But again, yeah, being able to dive into those really niche performance optimizations by using that pretty cool complex syntax is a superpower of the language, but it isn't essential for most use cases. And if you are building something like a basic web server, you can get away with just writing a very simple service in Rust and saving a bunch of money in infrastructure costs, having a faster, more reliable service, and it's just rewarding to build a fast thing. So yeah, here it is, transitioning from JavaScript to Rust and comparing the syntax. So for anybody familiar with Node.js and JavaScript, this is a basic HTTP server. This is using the standard library. There's no routing, no express. This is just, vanilla JavaScript, vanilla Node.js. We've got a package JSON, we've got an index.js, and all it's doing is saying, importing this HTTP library. I'm creating a server, writing a header, writing a response that says hello world, and then serving it to a port. And that's it, really. It's a pretty straightforward little application. Let me clear out all this stuff. And yeah, so running it, you can see this is the thing. And if we go to the browser and I go to localhost 4200, we'll see hello world, which is exactly what is written here. Now, obviously JavaScript is a very simple language and easy to use, but I also wanted to compare some of the performance metrics of this. And I'll do that at the end, but we'll look at memory consumption, we'll look at CPU utilization and that kind of stuff, and request responses, how many we can actually get, how much throughput we can get. But yeah, this is basically an HTTP server. So let's make it in Rust. So here I am on my desktop, and I use Cargo. Cargo, which is the NPM of Rust. With Cargo, you're able to install what they call crates, which are basically the same as NPM packages. And so this is like NPM init, so I'm gonna do Cargo new, and I'll call it HTTP server. And that's going to create a folder on my desktop called HTTP server. And then I'll just VS Code into HTTP server. Cool. And right away, you'll see a bunch of stuff. It'll automatically generate all the stuff, obviously, and you get a main RS. Now, in Rust, anything that's in a main function will execute immediately. So this is the code block that runs, and everything fans out from this main function. Whereas in JavaScript, anything you place in this block will run. But in Rust, you need to have a main function, and that's where everything kicks off. So we start out with our hello world, and if I go into the basics, we'll just do cargo run, which executes whatever's there, and in this case it's just printing print line hello world. Now, how do we turn this into an HTTP server? You'd think it's super complicated, but it actually looks pretty similar to the JavaScript implementation. However, one thing I'll give to Node.js and other languages like Go is they have pretty good standard libraries, whereas in the Rust world, you do kind of have to cobble together a lot of libraries that exist in the ecosystem. It does have a strong standard library for basic operations like working with arrays, working with strings and stuff like that, but something like an HTTP server, you gotta look out for that one. So in this case, I'm going to be using a library called UHTTP. And that'll install. It's got some stuff like JSON parsing and stuff, but we won't worry about that for now. Then, just like in JavaScript where you have import, in Rust you have use, and we're going to use UHTTP and HTTP1. So we're effectively taking this namespace, or it could be an object, it could be a function, it doesn't matter. In this case, it's a namespace, out of UHTTP, and this has a bunch of things on it. It's got a function called createServer, which we'll take, and we're going to pass in a function to it. So this is effectively the same thing as where in JavaScript you would do like a Lambda function. This is the same kind of thing. It's just a shorthand for function, and it takes a request and a response, and it returns a future. So in Rust, a future is basically a promise with some caveats. And the way that you denote it is you use async and then a block. And you can kind of think about this as effectively the same thing as saying like new promise res, kind of like that. So we have our callback, which runs the stuff, and then it returns a promise. And then in that promise, we're going to do res.header.set, and we are going to set our content type, and that content type is going to be text HTML dot await and question mark. I'll explain that syntax in a second, and then we're going to do res.write, and we will write the same output as we did in JavaScript. Cool. It's complaining because it expects a return type, which I'm not providing, and I will. And write requires bytes, so this one needs to be as bytes. And there is a shorthand where you can just say this string is bytes by literally just putting a B in front of the string, and then it's gonna be a byte array. Not found in this scope. Cool. Now there are a couple of things. You'll see some squigglies. Literally a couple. The first one is res is borrowed, and res must be mutable. So in Rust, values are immutable by default, and you must explicitly specify that they are mutable. So if I, for instance, define a variable like foo, and it's a string, foo can be used and passed around however I'd like, but if I want to mutate foo, I need to say let mute. So it's kind of like the difference between const and let in JavaScript. The difference is it's deep immutability. So if you have an object, none of the properties on that object can be mutated unless the variable itself is defined as mutable. Now the second issue is we've got the squiggly saying the async block blah, 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 borrows a res. Now what does that mean? This is the borrow checker, the infamous borrow checker that everybody is scared of. And it's honestly, it's a very simple concept. It gets a bad rap, but it is honestly not that complicated. So here we are in JavaScript land, and I'm going to try to build an analogy using some familiar syntax. So in JavaScript, if you create a value, then you do something like set timeout, and then you console log that value. This is totally legal, right? It's completely fine to do this. You can also then console log the value again, or do another set timeout and console log it there. This is not allowed in Rust. What's actually happening in Rust is when a value needs to be passed into another scope, the value's ownership must move. And the way you can define ownership is basically the function body or scope that the value is defined in is its owner. And in this case, value is owned by the function body of foo. It's not owned by this callbacks function body. Now, if I want to move value into this callbacks function, into this callback function scope, in Rust, this is not obviously like valid JavaScript, but in Rust you have a special keyword called move, and then it's basically going to say, hey, this value is going to be taken out of this top scope and moved into this inner scope. Now what that essentially does is it deletes it, like not actually, but like practically speaking, it deletes it from the top level. So it's like unplugging or undeclaring this variable as soon as it's been moved. So when I say move, it's gone. So that means the second console log will not work technically. But obviously Rust will say, oh, the value's been moved and you can't use it again. So the compiler will catch this move error. And that basically ensures that you only ever have one reference to a value at any given time. And that's really helpful when it comes to concurrency and the sorts of race conditions that you see in languages where you have parallelism, but you don't have any safeguards around it. Cough, go. But yeah, so that's kind of how it works. There's also the issue you might ask of like, well, what if I have two set timeouts and I need to use value in both of them? You can do some crazy shenanigans with the way that Rust does references, but there's a simple way is basically you put it inside of a box, not an actual box, but there's a value called RC, which is a box type, which takes a value and allows that, it like holds that value inside of its own kind of garbage collection zone. And then you can take that value and you can move it into multiple contexts. And as long as there's, it will stay in memory for as long as there are references active to it. And then when all the references are gone, it will drop it. So that gives you multiple references in multiple contexts. And then if it needs to be mutable, you wrap it in a mutex. Or a read-write lock or something like that. And now that gives you access to the value in multiple contexts, and it's read-write, and it's, But in this instance, we're not going to worry about that. That's just kind of how you would handle the multiple, where you have multiple scopes that need the same value. Back to Rust. So what's happening? We have this res value. It needs to be, it's going from this top level scope into this new promise scope. And so in order for us to pass this value into this child scope, we need to tell it that it must be moved. And so now res is defined in this callback function, and then it is moved into this nested scope. And then you do res write and res header, whatever, right? And that's pretty much it. For the most part, that's pretty much all you need to do to, at least syntactically, to get the server running. And that looks pretty similar to what we have in the JavaScript world. Now, the second part that's complicated is what's all this await stuff and how does all of that work? And why is it on the end of the expression? Also, what is this question mark? So we'll start with the await. There was a debate when they were designing this await syntax about where should we put it. Should we put it like other languages in front of the command or in front of the expression, or should we do something else? They initially wanted to do this, but the issue was when you put it in front and you want to await something and then access a property from the awaited value, you have to then wrap the entire expression in parentheses, and that can get pretty ugly, especially if you have multiple awaits and you're chaining them together. So they decided that it was better to just put the await at the end of the expression under a dot accessor. Okay, cool. So what about this question mark? The question mark is essentially like a try-catch propagate type thing, where the real value that's returned without the question mark is known as a response value, or result value, sorry. And that result value is, it contains an error, it contains two states, an error or an okay. And if it's okay, so like if let okay, value equals res. And then if let error is res. So you can kind of extract that value. Now typically you wouldn't use these if statements, but that's basically what's happening. We have this multiple value, we have this object that comes back and it's got multiple possible options that it can be, and that's all it is. If it's an error state, then the question mark unwraps it. It basically says, okay, if it's an error, send that up to the top scope, which will then send it up to the top scope, and let it be handled by whatever. And in this case, the create server will handle it. So if it comes back as an error, then create server will just return a 500 response. So we don't need to worry about the question mark. And we've talked about what the await, like why the await syntax exists. Now, if I run this, it's not going to work. It'll probably build, but it'll probably crash. Or do nothing, it just dies. So why is it dying? The reason it dies is because create server returns a future, which is the Rust equivalent of a promise. So I have to listen, obviously. And we'll do that. And then we have to await. This also now requires the main function to be async, and it's warning us because it returns a value that we're not using. And yeah, so we have to await the server starting off. So why is there an error on main? It's saying that the function isn't allowed to be async. Now, what's happened here is essentially Rust defined an interface for a future, well, you can think of it as a promise. It defined the interface for a promise, but it didn't supply the implementation for the promise. So what that allows is library developers, like this UHTTP library, to develop against that interface, expecting that if you need asynchronous behavior, then that will be supplied by the consumer, which in this case is me. I'm writing the server. But it isn't provided by default by the language. Another way to look at this is if you had in JavaScript an interface that was a promise. I think it returns a promise, right? Yeah, but basically, like you have this interface for a promise. But imagine if the JavaScript runtime didn't supply that interface. That's quite similar to the early days of when promises existed, where there was this design pattern. There was an interface, but you would have to supply a library like Bluebird or something like that, which actually supplied the implementation for the promise. And then obviously later revisions of JavaScript embedded that promise implementation within the library, within the runtime. But yeah, early days you had to supply yourself. And in Rust, you have to supply yourself, mainly because it's heavy. Like you have to supply it, so it's going to take up bytes in your binary. So if you don't need it, you shouldn't use it. But we need it, so we're going to use it. The most popular one is Tokio. There's others. There's like small async, STD, and a bunch of things like that. But I'm going to add Tokio. And I'm going to say add all of the features because we're not going to use all the features, but we'll just add them all anyway. So it's got things like FS access and bytes and some synchronization primitives and things like that. But we will only use a few of these features. Now the actual main function still can't be async, so it needs to be synchronous. But we need to call something asynchronous within it. And the way to get around this is basically to say main async, and it is an async function, but we're missing a main function now because we've obviously renamed this to something else. So we need to define a main function, and we need to kick off that Tokio runtime. So to do that, we go Tokio runtime builder, new multi-thread, enable all of the features, build. And then that's going to give us a result. And we're going to take our result and we'll match against it. And if the result is good, we have a runtime because our runtime successfully built. It can fail if like there's a runtime that's being constructed inside of another runtime and weird things like that. So it is possible for it to not spawn, but if you're doing it like this, it'll always work. Then we're going to block on this main async function, which once executed will return a future. So we'll execute the function, it will return that future, and then we'll block on that. And if it errors, we'll just panic. Cool. So what we're doing here is new runtime, and then once the runtime is running, it injects that promise implementation or that future implementation. Then we run our main async, and then it'll spawn our server and do the thing. So if we go cargo run, and we take a look at our browser, we go to 2000. Oh, let's just change this. We'll see that we have our Rust implementation working. Cool. But this is pretty ugly. Like, we don't necessarily want to see this every time. And it is a lot of setup. So is there a way to get around this? And the answer is absolutely. So Rust has this templating syntax. They're called macros. And the idea is basically code generation at build time. So Tokio provides this macro. And what that macro does is let you define a main function. And like, long story short, the macro is literally just at build time, it just pastes in code, it replaces itself with the code, and it does something. For instance, it might like literally inline the block of code from below or something. But as consumers, all we see is Tokio main and an async function. So if we go ahead and run it again, it should work. Now all this is pretty ugly. There's a little bit, oh, it's not that ugly, but it's a little verbose. Like, I don't want to see all these brackets and stuff. So Rust lets us simplify things a little bit. So just like a Lambda function in JavaScript, you can omit the brackets and have the return value be whatever is there. So that's effectively the same thing as saying like blah, and then returning a new promise. And then you don't need to provide a return explicitly. I found initially it was very challenging to understand when there were missing return statements. I felt like that was a little bit janky. But over time, I've kind of grown used to it, and I don't mind it so much anymore. I kind of prefer it, actually. But that's pretty much it. That's the HTTP server. And if we compare the two, you'll see that they are not that different. Ta-da! We have our create server, set header, write, end. Well, it's not necessary in the Rust context, but end. Now the cool thing about the Rust side is every time this endpoint, or every time this this callback is run, it's sort of load balanced against a whole bunch of threads. So if you have like 16 threads on your machine, it's going to run against 16 threads. Whereas obviously the JavaScript implementation is only running on the main thread. So you'll saturate that long before you have the ability to. You'll saturate that long before like the machine will still have capabilities basically. But yeah, so the increased multi-threading capabilities of Rust is fantastic. It kind of comes out of the box. It's what they call fearless concurrency, where you don't need to worry about race conditions. Everything will just be, if it compiles, it'll work. It's pretty great. So you can write super fast applications, and you don't necessarily need to worry about anything, really. Unless you use unsafe, but you know, barely anybody uses unsafe. That's very niche. That's only when you're building like embedded systems or doing systems programming or mapping to, you know, system libraries and stuff. But Node.js does that behind the scenes in these libraries, and you know, it's the same thing really. Just you don't see it. You interact with high-level APIs. But let's look at the numbers. What do these servers look like in terms of memory, in terms of performance? So I'm going to run the release build of the Rust application. And this can actually be tuned further just by setting some flags on the build. And I will run the Node application. It is already running. Good to know. So just to confirm, we have Rust on 201 and Node on 200. So I have an application called Oha, which does stress testing on HTTP services, and I'll just slam the services with it. This is the Node.js service, and we can see that there are a bunch aborted due to deadline. These are probably at the tail end of the requests, but it's okay. And yeah, so we've managed to transfer 10 megabytes in total. We got 75,000 requests per second. And the average time sort of doesn't matter, but the P scores do. So the 4 nines is like 4 milliseconds, and then it sort of dips down to 1.5 milliseconds, and so on and so on. And if we look at the Rust side, we can see that Rust completed almost 300,000 responses, whereas the Node.js only got 45,000. The 4 nines was 1 millisecond versus 4 milliseconds. And we got an average that was 0.1, which is compared to 0.6. And yeah, we got, again, 400,000 requests per second versus 470,000 versus 75. We also obviously transferred way more data because we got more requests per second, and the payload size was the same. Size per request, 24 bytes, so pretty similar. And yeah, I guess there's probably some aborted again, just due to the tail end, probably just sockets not closing and all of that stuff. What about memory usage? So if we open up, let's do another tab and do Zenith. And I don't have any fancy tiling. I should learn it, but I never really got around to it. If we look at index.js, our Node.js server uses about 70 megabytes of RAM, which is honestly like, that's kind of nothing. It's pretty good. And then if we look for cargo, I guess would be, I wonder what it would be. HTTP server. Oh yeah, here it is. Yeah, so our HTTP server is using 3 megabytes of RAM. So yeah, pretty good. But yeah, that's pretty much it really. Thanks everybody for watching. If you made it this far, like, you're awesome. Thanks for watching this video. It's been a long time since I've made a video, so yeah, again, I appreciate it. If you guys want to see more content like this, like, let me know. I can do some deep dives into more of the semantics. I kind of rushed this one and brushed a lot of ideas and stuff off, but yeah, let me know if you liked it. Like and subscribe, and leave a comment for the algorithm and all that stuff. Yeah, cheers. See you.